Welcome to this explainer made by Forge College. I am absolutely thrilled to have you here today. If you were with us for our last session, you know we had an absolute blast tearing apart the anatomy of a block and the ledger. We saw exactly how transactions get packed in, sealed up with cryptographic hashes, and locked into an unbreakable chain. But actually, that kind of left us hanging on a massive cliffhanger, right? I mean, we've got this beautifully constructed, mathematically perfect block just sitting there on a single computer. And honestly, what good is a shared ledger if it isn't actually, shared?
So, okay, let's dive into this. Taking an isolated block on your local machine and distributing it securely, accurately, and at lightning speed across a global network, that is a massive, massive engineering challenge. It's literally the plumbing that makes Web3 actually work in the real world. Today, we're going to look at the incredibly clever ways these networks are wired up to make sure that everyone, everywhere, agrees on the exact same version of the truth.
Here's our blueprint for today. We'll track how a block's journey begins, meet the network nodes, explore the art of blockchain gossip, compare permissioned versus permissionless setups, and wrap up with trust, resilience, and availability.
All right, section 1, the block's journey begins.
Remember, a ledger is completely useless if half the network thinks Alice paid Bob and the other half is absolutely positive Alice paid Charlie. We need a rock-solid, standardized process to get everyone on the exact same page. So here's our 4-step assembly manual. First up, someone has to propose a block. Basically, they bundle up the latest transactions and shout to the network, "Hey, I've got the new updates." Second, their immediate peers validate it. They check the math, check the logic, just making sure there's no funny business going on. Third, we propagate. Those peers forward the block to their friends, and so on. And finally, step 4, the block is stored for good in everyone's local copy of the ledger.
Moving on to section 2, meet the network nodes. Let's see how this builds out. I actually love comparing these network roles to an office environment. Your full nodes, they are the meticulous record keepers. They store absolutely everything, every single transaction since the dawn of the network. They trust absolutely no one and verify every little thing. Then you've got light clients. Think of them as the busy executives. They do not have the time or the hard drive space to read the whole 500-page report, so they just download the headers to get the executive summary. Then we have validators, or miners. These are your noisy idea generators, the ones actively competing to propose that next block. And finally, the observers. They're kind of like the summer intern, just quietly watching the data flow by, maybe feeding info to an analytics dashboard, but not actively validating or storing the deep history.
Which brings us to section 3, the art of blockchain gossip.
So, we've got our block, and we've got our cast of characters. But how on earth do they actually talk to each other when there's no central boss dictating the rules? Well, they use what's brilliantly called a gossip protocol. Think about it. If you have a juicy piece of office gossip, you don't call an all-hands company meeting to announce it, right? No way. Instead, you whisper it to 3 random friends at the water cooler. Then they tell 3 of their friends, and boom, within hours, the entire building knows. This peer-to-peer method is exactly how nodes randomly share ledger updates. Now, what's really interesting here is this concept called a fan-out multiplier. Let's look at a multiplier of 0.5. If a node has, say, 10 connections, a fan-out of 0.5 simply means that node will randomly pick exactly 5 of its peers to whisper the new block to. It's just a way to quantify how chatty the network is. So what's the actual impact of that? Well, if you tell fewer friends, a low fan-out, you end up saving a ton of network bandwidth. It's quiet, it's efficient. But you do run the risk of the rumor just kind of dying out before everyone hears it, leaving some nodes completely in the dark. A high fan-out, on the other hand, creates incredible redundancy. Even if half the network suddenly loses their internet connection, the block still finds its way through because literally everyone is shouting it to everyone else. It's super safe, but, it eats up a lot more bandwidth. All right, let's pivot to section 4, permissioned versus permissionless. Okay, so we know how the gossip spreads, but who actually gets to walk through the front door and join the conversation in the first place? Here, we have 2 completely different philosophies. A permissionless network, think Bitcoin or Ethereum, is basically an open public square. Anyone, and I mean anyone, can join, read the ledger, and try to propose a block. Versus a permissioned network. Now, this is your private, bouncer-guarded VIP club. You have to be on a strict allow list just to get in, which, as you'll see, completely changes how blocks get validated. Because identities are known and vetted in a permissioned network, you don't necessarily need all that chaotic random gossip. If you only have a few highly trusted VIP validators relaying the blocks, the spread of data is lightning fast and super predictable. But, and this is a big but,
The trade-off is that it introduces single points of failure. If those VIPs go offline or get compromised, the whole network just stalls.
And that leads us perfectly into Section 5, Trust, Resilience, and Availability. You know, exploring these intricate network behaviors is a really huge part of what we do in the learning community at Forge College. And it all boils down to this one absolutely crucial concept: trust minimization. Everything we've mapped out today exists entirely to support this guiding principle. The goal? To build systems where we literally do not have to trust any single party or even a small group of VIPs to keep the whole machine running correctly. So, looking at this architectural schematic, it becomes pretty clear that every choice in a blockchain is a trade-off. Look at randomized gossip. It saves you bandwidth, sure, but your network updates might lag a bit. Full relay by a small group of validators? It's incredibly fast, but boom, you've got central points of failure. Permissioned access gives you great control over who gets in, but at the steep cost of centralized trust. The reality is, you just can't have it all. You are constantly balancing speed, bandwidth, and ultimately who holds the power. To really summarize the core difference here, you can choose immense, chaotic, beautiful resilience by pushing the responsibility out to thousands of independent peers in a densely replicated mesh. Or you can trade all that openness away to get highly controlled, predictable, efficient performance and a permissioned model. So, holding those network topologies in your mind's eye for a second, I want to challenge you with a thought experiment. What happens if half the office suddenly decides to start spreading a malicious lie? Or what if the power just completely goes out on the top 3 floors? Ask yourself, how easily could an attacker shut down the rumor mill in a highly concentrated permission network versus a wildly decentralized one? There's a quote from our source material that I absolutely love because it really grounds all of this theory. It says, "The ledger only becomes shared when participants exchange data. Topology dictates resilience." Think about that. The most brilliant, mathematically flawless block design in the world means absolutely nothing if the network's plumbing is broken and that block can't reach the rest of the nodes. So as we wrap up, I want to leave you with a bit of a provocative thought. As we look ahead to our next explainer, Synthesis of Blockchain Basics, ask yourself, can a perfectly decentralized network ever be truly fast? Or will the fundamental laws of network physics always demand a trade-off? If today's explainers sparked your curiosity, and I really hope it did, I highly encourage you to visit forge.college to continue exploring this massive Web3 rabbit hole with us. We've got so much more to uncover. Thanks for watching. This explainer was made by Forge College, and until next time, keep questioning the consensus.